So hello, today we'll be presenting this paper called Hopfield Networks All You Need. It is from these authors here and it was published in 2021. Of course, this title is like is very similar to the Attentions All You Need. That basically is the paper that introduced the idea of the transformers that we see like basically everywhere today. So this is not, of course, from random, like this is the try to establish a connection between this concept of Hopfield network with the transformer. And before I go to the notes and start explaining the paper, I would like I'll say like why I choose this paper and why I found this paper interesting. Basically, the transformer architecture is something that changes a lot of how we see language and how we see machine learning, and basically I think changed a lot of a bunch of things. And there's this old concept of Hopfield networks that I think it was introduced like in 1980s, and I think it was one of the first ideas how to model like the human brain on a computer. As we'll see, like this idea is closely related to how to model like the human memory on a computer. And I think it's not very well known by a lot of people because I think it was lost at the time. But this paper is interesting because it can connect like one concept and one concept that's very new together and see that they're really closely related. I think maybe on science this may happen a lot. Someone invents an idea way too soon, then when the idea can be like a breakthrough. So maybe that's what happened here. But just to say like shortly the abstract, this paper chooses a type of Hopfield network that has certain properties that are nice. We're going to see more details what is a Hopfield network and what are these properties, but basically it is a continuous Hopfield network and can store a lot of patterns. In fact, exponentially many patterns, given the dimension of the input. And the update rule of this network is like is the same as the attention mechanism of the transformer. And here they say like you can use this as a layers on the deep learning architectures and so on. They provide like a code for the paper, but let's go into the details later. Like basically, what is a Hopfield network? Let's start with that. Basically, as I said, it's a very old idea, and an idea that tries like to model the human memory in a brain. It's closely related to what is known as a neural network, and we can represent the Hopfield network as a graph, like with neurons, and these neurons has connections, as the usual. And it's very closely related, but the idea here is not like to make like a classification procedure or like a regression procedure, but storm patterns. So basically, I give this example here with like a binary Hopfield network. That's not the case of the paper, that is a continuous, but let's start with like the binary. So basically we have like I don't know if it's possible to see my mouse, but it is possible to see my mouse.
Yes, we can see your cursor.
Okay.
Yeah, good.
Okay, so basically we have like a list of binary strings that will be like the members of the network, and it's like 1 0 1 0 0 1 1, for instance. And basically the main idea is to pass like a input that we'll be calling here carry. The idea of this terminology is because it's very similar to transformer. I'm going to make like an analogy, right? And this carry will go through the network and we'll do something with like the weights of the connections and discover like a pattern, which will be a pattern that is stored on the network, right? So that's it. And you think about it, like this is idea, like the idea that let's go back like to the human brain, like this makes like an assumption that every neuron or brain is connected with every other neuron, and besides that, it's very similar how we do with memories, right? For instance, imagine if your grandmother used to make like a very good food with a certain spice, and after years of our grandmother passed away, we start smelling that spice, and every memory that we had of our grandmother comes to our mind. Like in certain way, similar to how our brains use taking a certain very high level of how our memory works, right? So yeah, it's important to note here that this example is binary, and as we will explore, like for being binary, we have certain problems. For instance, we have very few possible memories. For each neuron here, we can have possible two states. So 2 times 2 times 2 times 2, 5 times, it will be like 32. So we could have like only 32 memories. This is not something very large. And yeah, but let's continue. Like this is like the basic idea, like the high level idea, what is a Hopfield network. Other concepts that are very similar to what is more well known in neural networks, the update rule and the weights. The weights would be like the number on the connection here. Right? It's something that reflects the state of network that will be used to retrieve the pattern, that retrieve the memory given a pattern, given a carry, right? There's other thing called update rule that would be like making like an analogy, would be like how we train the network with like gradients and something like that. It's not exactly a gradient in this case, but it's very important for the network, since this will be something that will be applying iteratively through the epochs to gather like the stored pattern. Right, so one important distinction to make is like the binary, that was the first, that I think it was like they introduced on the original paper of Hopfield, and the continuous. Here on this paper, they introduced like continuous Hopfield network. This, as we will see, will solve the memory constraint that I explained. Like this can only store like 32 patterns, but with like continuous, you can store a lot, exponentially many patterns. And yeah, basically this 110, now it's a continuous entity. And what is this continuous entity? Are vectors, right? So our vectors, and vectors usually represent as arrows in space that you're dealing with. So imagine that on this network, you don't have like more these binary strings, you have like vectors. And they're going to give like other vector, and you do something to retrieve a vector. So basically, this is the generalization that we want. So yeah, let's explain a little more like what's the update rule. The update rule of a Hopfield network is the only thing that we in fact implement in your code, right? We see that there's other concept associated with the Hopfield that's called energy. It will be like the loss function. But if you want to make like a minimalist code, we didn't have to implement that. We just have to implement like the update rule. And this update rule, of course, is associated closely with like the energy function of the Hopfield. Here you can have a lot of different energy functions, and it's not like the usual as you expect from the neural networks, for instance, like I don't know, cross entropy or something like that. You can have like something more different. And yeah, but if you want to make like an analogy, since the concepts are very similar, this would be like the loss. So here's one of these expressions here, like the first one of the most important expression of the paper. It's like for the classic modern Hopfield network. Right? It's the energy function of the classic modern Hopfield network. The classic, I put it here because I don't know if this is like the first energy proposed for a Hopfield network, but it is, I think, like the state of the art that this paper tries to expand. You know, So it's for binary strings. And here we have like exponential. LSE is, I don't think it's very important, but I think they define this as this function here. But we just have to know that it is a mathematical function, mathematical procedure. And for calculating an energy of a given state of the Hopfield network, we pass the carry, that is this number, this vector C. And X is the state of the network, or in other words, the weights of the network. Basically, this is important to notice that is like an inner product of the two vectors. So we're taking like the inner product and giving to an expression, mathematical expression, to get like the energy. And to retrieve like a pattern on the network, we have to minimize this, right? There are a lot of ways to minimize this. I think like the first and the most maybe traditional like gradient descent or something like that, but as you'll see, usually on this subject they don't use this, but yeah, the important takeaway here is that you have to minimize this energy if you want to retrieve like the memory stored on the network. So this paper introduces a new type of Hopfield network, as I said, that stores continuous patterns or vectors, in other words. So I think one of the most important figures of this paper is this figure one that translates like the main ideas of the multiplications that they propose for the state of the art. So there's this classic Hopfield energy, that is this expression here. And this they put like equal, it's not equal, of course, but equal sign means keeps the property. So they propose a new energy that keeps the properties of this old one, that we will see like which properties are there. And they propose an update rule that I commented, that is like the gradient descent. That is the expression here, and this is very similar to what you know as a attention mechanism in the transformer. So yeah, basically, I think these figures is very important to understand like the paper, and summarizes like the main ideas that they introduce here. So let's dive deep like into this idea here. So basically, for better understand like what it is doing, imagine that we have like stored patterns or memory, and this is represented in this box with all these vectors that will be like the patterns that we stored on the network. So basically, we pass, as on the binary case above, we pass like a carry, an input to the network, and to retrieve like something, a memory with this carry. Basically, you do this by picking the memory that's most similar to the carry. The vector on the memory that's most similar to the vector that you're passing as a carry. And in other words, as I said about the inner product, I think this is very important to have in mind, like what is an inner product? Because we're trying to maximize this. And basically, we are going to pass the carry and try to make like an inner product with each one of these vectors here and gather like the vector that maximizes this inner product. And for this, we apply the update rule multiple times. In other words, we apply this update rule that they propose a lot of times until convergence. Put it that way. And after that, we have like the memory. So this is like the basic procedure of what is like a continuous Hopfield network. Yeah, and if you studied or saw something related like transformers and attention, basically, I think like you see like certain relations with like the attention, like what is that attention? Like in transformer, like you pass like a sentence, for instance, and hi, how are you? And you pick like each token of this sentence and transform it to a vector representation, and would like do operations, linear algebra operations with like inner products too, and calculate like weights for each of these tokens. For instance, you'd pick like, hi, how are you? So you'd pick like how, the word how, transform this into a vector, and every other word into a vector, and calculate like this attention, and this attention would output like weights for each one of the tokens. So this would be like the attention of the transformer. So it's very similar. Basically, we're doing like the same thing. So, but for the transformers, we're doing this only once, and like here we can do this multiple times. So, but yeah, like this is like the basic idea, and I hope like it's more clear like the connection now, but we'll explore more here. So yeah. Here's the image again that I commented, like the most important image. And yeah, I have like this new energy that they introduced. This derives like the update rule that you run. That is very similar to transform attention, that the equation per se, that is basically this beta that you can interpret as an hyperparameter thing, and X is the state of the Hopfield network, and C is the carry. And softmax basically is like a way to normalize this, to have like values between 0 and 1. One thing that I want to highlight here is basically the fact that for introducing this update rule, we don't have like to modify a lot of this indication. That is something that I found interesting. So basically on the classic Hopfield energy, we just have like to add some term that is plus this quantity here, and plus C. C is a constant. It doesn't matter for like optimization. It's a constant we can ignore. But basically, just have like to add this term here, and we derive like an update rule that is very similar to the attention mechanism. But one question that I had written today, but I think they reversed engineer, because I don't believe like they first derived the new energy, and then after that they found update rule equals transform. No, I think like they looked into the attentions I unit paper and try to reverse engineer the process to find like a Hopfield hot network. I don't know, maybe we'll never know if this is true or not, but for me it makes sense. Like, since we know for this intuition that it's very similar, the two ideas, you know. So yeah, but we never know. So yeah, I wrote here one of the main takeaways, like, I don't know if you forgot, if you end up forgetting everything of this meeting, but maybe you can just remember this phrase here. You can look at the attention mechanisms as a Hopfield network. Basically, this is like one of the main takeaways. But yeah, and now with this idea and with like an understanding of, let me ask like if there's any questions. If you don't have any comment, because now we will be showing something else.
I guess you can continue.
Okay, so basically this is like the high level approach of what is the concepts that are introducing here. But now let's see a diagram that they put it on the paper that I think it will be helpful. I try to implement these ideas like with like a Hopfield network. So they introduced on the paper this idea of like a Hopfield layer that can be integrated in usual architectures, like deep learning architectures. And this is like the flow chart, what this Hopfield layer is doing. Basically, it's again very similar to the attention mechanism. Basically, you pass like certain inputs here, R and Y, that reflects like the state of the network and the query that we're passing. So basically, this would be like the input, After that, you do some normalization. I don't think that's very important to understand, but here we project. This project basically is the operation, the mathematical operation that you do for getting like the keys and values of the transform. Basically, for doing that, I think you have to like just multiply with like this matrix W key, W value, right? And after that, you obtain the key value per se, and you go through this match move, scale, mask, softmax. Basically, this translates, I think, to the update rule, right? This translates to this update rule here, softmax. And after that, from until now, basically it's the same as the usual transformer, but we have like this final idea here, like multiple updates. This only makes sense if you see like the attention as an update rule of a Hopfield network, right? So if you can say no, then finish the procedure and have like the usual transform. But if you say yes, you'll be obtaining like the key and the carry, and you'll be doing these multiple times to retrieve like the pattern that you want in the network, giving a query, right? So I wrote some things here. Intuition, each input set outputs a key and a carry. That's right. You pass like the pattern that you're passing on the Hopfield network and the state of the Hopfield network, and to have like the query and the key. The value, if you see like on the chart, is very redundant with like this other one with the key, right? Yeah. Yeah, and for better understanding this, I put an example here with like maybe with like a sentence, and imagine that this is passed into this flow chart here. So basically, the sentence in my cat is very pretty, right? So this will compute after I pass this with the previous states of the network, certain keys and carries, right? That will be vectors on representation. And basically the Hopfield stores the key, and with the dot product being the update rule, we treat the value we want, right? So for this example over here, imagine that we're focusing our attention on the cat vector, the cat word. Basically, this would do like a linear product with every other query vector over here, and you get like a value, like a number. Certo? For this example, the cat vector will do an route with every key carry, and then we'll normalize softmax, right? And then to applying like the softmax procedure. Since we're getting like a number for each other token here, we can plot this for helping us understand what is going on with like an histogram. And this histogram here would be something like this, right? So basically would attribute weights for each other token over here. And we expect that a certain token, a certain word would have like the most concentration of weights. In this case, I put like the concentration, the attention on the pretty. So we have like a histogram like this on this attention layer. So cat have attention pretty, and here's where the attention is located. This type of understanding of the attention as with these histograms would be useful because they further on the paper they did some experiments and analyze the bird model, and you see like these histograms, and very interesting. But let's continue. Yeah, I put it here other interpretation of what's happening besides the histogram that is more related to vectors, like a more geometric interpretation. We'll be applying the since we're interpreting the attention as an update rule of the Hopfield net. Basically, you can apply this multiple times, the attention multiple times, and basically what is this doing if you think like on vectors. Basically, you have like the theory and the key. On the first iteration, we will have like a new key, right? New key. And this key will be like the weighted average of the Q and the key. So we have like this blue vector here for the iteration one. After applying another iteration, we will be taking like the weighted average each time. So basically, we every time we're getting closer to the Q, right? So yeah, I find this there's like two different ways to interpret this what is happening in this flow chart. You can interpret like this as like a histogram or the vector, as I said. And by applying these like multiple times, you can ask another thing, like what will happen like on the histogram of the weights, as I put it here. One thing that will happen that they propose on this paper that the histograms will be, with each update will be more concentrated in just a single point, right? All the mass of the histogram will be concentrated in just a single token, so all the attention will be in a single place, right? So that's one interpretation that they give, like of applying like the update rule multiple times in a Hopfield net. And besides that, on the real world, of course, this is like I think like the perfect world, right? We have like just one attention for one word, but on the real world, of course, we can have like other types of histograms, and they proposed two other possible histograms that you can get, like one that they call the net stable mode, that basically have like attention on a very low attention on the majority of your tokens, but some tokens have like a very high attention, and the other ones more like an uniform distribution, right? Basically, you don't have attention anywhere, just have like attention everywhere. And this will be used for later on to understand some experiments that they did, but from now we can move on. The paper, one thing that I liked about this paper that they provided like a code for the idea that they proposed, but they provided a theory as well. So basically you have like a complete paper. Maybe that's why it has so many pages. But yeah, they have like 60-page appendices of proofs, and of course we won't be diving into that, but I will just pass like to the main theorems pretty quickly, and just have like the intuition of the properties of this Hopfield network. So basically, the first theorem establishes a connection between the update rule that I commented that equals the attention mechanism of the transformer with the energy function that they proposed, like established like, because here you have like we have like an arrow, like this energy translates to this update rule, but this is of course this have to be like you have to have like a strong argument for why is that, right? So this theorem established this argument by indicating that you can minimize the energy function by applying this update rule, right? So this is the idea of the theorem. Basically, you're saying that this converts some. Theorem 2 is basically the same, but with another idea of convergence. So the first one introduced like the convergence as something related to the energy. Here, we are only looking at the C values of the network, the Q values of the networks, and we're seeing that this comes closer and closer as we are applying the update rule. So it's another way to tell that you're converging somewhere. And I think with these two combined, have like a strong sense of convergence of the algorithm. The theorem 3, I think it's more complicated, but I think it's more important. But the theorem more complicated, and before introducing the theorem, they introduce like a definition of what is like a pattern that is stored and retrieved. like when you can say like the pattern can be stored and retrieved, right? So basically, this definition is related to the idea of sphere. So basically, imagine that every blue dot here is like a pattern, right? So you can say like that a pattern can be stored and retrieved if you can like separate the patterns on the space that you are putting the pattern. Like, and this translates to drawing like spheres that won't intersect with each other, right? So basically, you can draw like spheres that can intersect with each other on the patterns. We can say that the patterns are well separated, and this is like a good sign. You can like store and retrieve. But there's other thing that they introduce definition besides that to check like if a pattern can be stored and retrieved. That is, if I start with like a C anywhere on the space inside the sphere here, for instance, this one, what I expect this converge somewhere inside the sphere, right? And this applies to every point on the sphere, right? So basically, if I start on the sphere, it applies this update rule multiple times, where I end up on the sphere. Right? Here it's important to note that maybe the convergence will be not exactly the pattern that were stored. Maybe there's an error here. And they call this error the retrieval error. But yeah. And yeah, about the theorem 3, this was just the definition. The theorem 3 established like how many patterns you can store on the network. So basically, it says like if failure probability of retrieval a variable of p, and p being a value, since it's a probability being a value of in 0 and 1, and p being small, so there's a small probability. So basically, you have like with probability 1 minus p, the number of random patterns that can be retrieved is this one, n, and n is greater than c, there's a constant, times d minus 1 divided by 4. I think this expression is not important, but the important here is that we have like a d on the exponent of something. So basically, if I increase d, I increase a lot the patterns that will be possible to start on the Hopfield net. So, and d, what is d? D is the length of the space that I'm putting on the pattern. So the length of the vector. So yeah, this solves a problem, the classic Hopfield nets that I commented about the how many patterns you can store. Right? Okay, so I established some ideas related to the convergence, but one important question to have, like, but how fast does this converge, right? And this theorem here, I think it's very nice because it says that converges really, really, really fast. And so fast that converges with one iteration in most cases. So this is interesting because from what I introduced here, basically this is like the same as the attention mechanism transformer, but we have like this last step here that we can apply like multiple updates, right? And one question that someone may have like reading this paper, okay, so since we're applying these multiple times, why does like, since you can apply these multiple times, why does like, if I apply like just once, the transformer will work, like? And this theorem explains this, basically because you have like this very, very fast convergence, basic instantaneous, right? So yeah. And basically you have like this inequality here that translates this distance with update. This is the term here. Distance with update is less than distance at the previous update, on the current state. And so the next state will be less or equal to a constant times the distance in convergence of the current state. So, and there's this term here that have a lot of terms here, but doesn't matter because we just have to look that there's like an exponential here. So basically you have like this constant here that will be proportional to a constant, and you'll be dividing for exponent, exponential term of like a big number. So this will be very, very small, like 0.0001, 0.0000, a lot of zeros, one, and I'll be multiplying with like the previous distance of the convergent, the distance in the convergence. So I have like a really fast convergence. And this is nice because it answers another question, like, okay, I know like a transformer have like multiple layers. So basically this paper introduces the idea of applying the update rule, that is basically the attention mechanism multiple times. So this would complicate even more the training of these architectures like BERT now, because you have to apply, it would be even slower because it would have two for loops concatenated that way. One related to the update rules and the other related to the layers. But yeah, we don't have like to apply two because we have like a strong, it will converge really fast. And so, yeah, how many iterations needed at each layer? Very low number in most cases. And the last theorem is another bound that he proposed. Again, you just have to observe on this inequality that has like this exponential term that will put this to a very low number, this will result in a very low number, and this term here, that is the retrieval error, will be even smaller than this small number. And retrieval error, as I commented before, this error here, it's like the error of the convergence, right? With like the real start pattern. Yeah. Yeah, the above is bounded. Very nice. So they did some experiments too on the appendices. They put it there, and basically they did a bunch of experiments. They tried to integrate this Hopfield layer, as I commented, through certain tasks, and they achieved like nice results, like with like state of the comparison that they made. So for instance, this one here, they achieved like a nice result with the metrics that they proposed. And for this multiple instance, there is this immune repertoire classification that they applied one layer that proposed that Hopfield polling and achieved nice results. But I here will be focusing on other experiments that they did. They picked up retrained BERT model from the Hugging face and analyzed those histograms that I mentioned before. With the attention, like these histograms here, like of the attention rates. And okay, so they plotted the histogram for different heads and layers of the BERT. And then they looked at these histograms and like they made one question, like, how many patterns do I need to reach like 9% of the histogram mass, right? Because if I can answer that, I can like characterize the state, like which for each layer and each head, like in each state I'm dealing with, like I'm dealing with this state with like all the attention focused on one on pattern, or I have like a dispersed attention or something, like I'm at a stable mode with like different attention and different things. So yeah, they plotted this figure here. I found very interesting that goes for each layer, like here's layer and here's head. So with that, like the histograms that I commented. So for instance, we have certain histograms that translates like to full attention on certain aspects of the input. For instance, this one here. There are others that have like this bimodal attention, like this one here. Others that's very similar to a uniform thing. You don't have attention anywhere. And here you can see clearly like the these different behaviors. One thing that is important to note here, like the layer 1 is this one. So basically layer 2, 3, we are going into the bottom to the top, right? And yeah, one thing that caught my attention here is like the first layer, we don't have like any specific attention. Like basically the bird's not looking at anywhere. They have like a very dispersed attention. And as we go deeper into the architecture, we are now dealing with like basically the birds start looking into certain specific aspects of the input. So maybe like this is like pre-processing, this is like thinking, because something like that. And yeah, this last layer have like something very similar to the first one. So, the histograms above, the histograms above show the behavior that I commented. And one other thing that I wanted to add here about this experiment that they did is basically like a possible explanation of why we have like these histograms. Why certain histograms are more like a uniform thing, others are more like a bimodal thing, and others are totally concentrated in a single point, right? So basically, the idea that introduced here is more related to the concept of these spheres that introduced a certain definition of a pattern that can be stored and retrieved. So basically, in the real world, you can have like overlap of these spheres, like this draw that I made here. And yeah, basically all these spheres are on the same place, and imagine that you start somewhere on this fuzzy, this messy thing. And you can ask like, okay, so, if I apply the update rule multiple times, where I will converge on this thing. So basically, I think the intuition basically will converge to the somewhere on the average of the center of the spheres, right? Would be not converging like to a specific pattern, but to somewhere like in the middle here, that's like the average of the center of the spheres, basically. And this translates basically to maybe to the idea of like having like a uniform histogram, right, over here. So maybe that's the explanation why we have like uniform histograms on this bird model, because we can't like the patterns that are stored are not very well separated. You know? And the formatted stable case, we have maybe something like this. We have like the same cases above, so but with different clusters, right, of different stored patterns. So basically, this is like clustering, right? And we start somewhere on this space and apply the update rule multiple times. We're not anymore converging to a certain pattern stored. We're converging to a cluster, right? And the result on the histogram and the bird model notation, maybe it's something like this. Like we have like this a very low value for a lot of tokens, but certain tokens have like a spike, right? And maybe the intuition behind this, like each cluster represents something like the verb. Like you start somewhere and you ask yourself, is there a verb around? If there's a verb around, go to the verb cluster, right? So yeah. But yeah, I don't think I did propose this on paper, but yeah, I think like this is like an open research question. And to fully understand like the dynamics of what's happening there is like an open research. It's not like a final explanation of what is happening. And finally, there's one last experiment that I wanted to show here, but I think it's better to show it on the paper. Let me find. Yeah, I found this plot very interesting. It's basically the same as the above. We're plotting like the histograms, of each head and each layer. But now we're looking the histograms at each iteration of the training. And yeah, we have like certain behaviors here that I think are very interesting. For instance, we have like this behavior that totally drifts from a certain point to another. There are other behaviors that, for instance, this one basically starts as a total uniform distribution and then goes and concatenates just into like the first histogram that I showed, like the attention fully focused on a certain aspect. And I think there's the opposite case somewhere here too. Like it started totally focused, and after that goes to I think there's not this case. But yeah, I think like one nice area of research is like to understand like these dynamics here. Like I think it's not very well established if I continue the iterations, these will continue being this graphic, like it converts or it will change to something else. I think like this paper opens some interesting questions to understand like the attention mechanism, right? And by seeing the attention mechanism as a Hopfield network, I think we're seeing the attention mechanism as something bigger in a certain way. So maybe we're trying to end up like generalizing the idea of an attention mechanism. And I don't know, it's another question, like an open question that I don't have like the answer. But if like we propose other energy functions here, like one interesting question to have, can we derive like other types of attention that have like more interesting properties, like insert, sorry. Here, you like propose other types of energy for other types of Hopfield networks, can maybe derive like other update rules that can give maybe like better properties for the transformers. This is another question that maybe this paper introduced. And yeah, and as I commented, there's this repo here. I didn't have like much time to think with like the Hopfield nets, like make like a notebook, but basically I think it's very well encapsulated, like the layer. So basically, I think there's no the usage very simple to use these Hopfield layers that they introduced with like common architecture, right? And since this is like a continuous sync, you basically possibly can apply like back propagation or based in the sense because it's like continuous. So basically you can train these with no problems maybe. And yeah, here they propose like examples. Generally the Hopfield layers designed to be used to substitute different layers, like they propose this idea of substituting like polling layers, the GRU, LSTM, attention layers. And from the paper that they showed on the experiment session, they had like nice results with the tasks that they tried in comparison to like other architectures. But yeah, I think like that's the main idea of the paper. I don't know if I left something out.